Hello, linear algebra students. Today's video lesson is on the determinant of a matrix. Now, an elementary product of an n by n matrix A is a product of n entries such that no two entries of the product are in the same row or the same column. Now, first notice that this matrix A has to be square, has to be n by n, and the elementary product must involve n entries. So let's focus first on this 2 by 2 that we see right here. You could ignore what this DET means for the time being. Just focus on this 2 by 2 matrix. And I want to create an elementary product. So I'm going to just grab any old entry of this matrix. Let's grab this A11 to begin. And then include that in my first elementary product. Now I need to have two entries being multiplied in order to be an elementary product of this 2 by 2 matrix. And the next entry I pick cannot be in the same row or column of the entry I've already picked. And so that means we really only have one option for the second entry we pick, and that's this A22 position. And so we would get A22 is the next entry I must pick, and we have an elementary product, A11 times A22, and neither of these entries are in the same row or column. The next question is, are there other elementary products of this matrix? The answer is yes. If I involve this entry here, A21, and then I must involve a second entry that cannot be in the same row or column as that, so that must be the A12. So here's a second elementary product, and I'll write that next to this. These are the only two elementary products of a 2 by 2 matrix. Okay, let's go back to our reading and read this next paragraph. First, order the terms of the elementary product by row index. All right, let's do that first. So looking at the first elementary product, the row indices are the first numbers. And notice that this elementary product, the terms are already ordered so that the row indices are in increasing order, 1 and then 2. So I don't need to rearrange these terms. Let's look at the second elementary product. The row indices are 2 and then 1. These are not ordered by row index, and so I do need to switch the order of this product. It's still an elementary product, but I'm just going to put the A12 first and move that over. Okay, now let's continue reading. If the column indices of the entries of the elementary product require an even number of interchanges to be sorted from least to greatest, the elementary product should be multiplied by 1. Otherwise, the elementary product should be multiplied by -1. This creates a signed elementary product. All right, so looking at this first one, now let's focus on the column indices. So that would be this 1 and this 2. Now notice that they are already sorted. So it requires 0 interchanges of these numbers to sort them. So I don't need to move this over here, for example, because they're already sorted. So 0 interchanges to sort the column indices means that, and 0 is an even number, means that to create a signed elementary product, I'd need to multiply this by +1. So I'll just put a plus sign to indicate that we thought about that. Now let's look at the second elementary product. Focus now on the column indices. Notice that they are out of order. We have a 2 and a 1. So this would require 1 interchange of these numbers. There's the interchange. We switched the 1 and the 2 in order to order them. And 1 interchange is an odd number, and an odd number of interchanges required to sort the column indices means that we should multiply this elementary product by -1. And these are the two signed elementary products. Now let's read this third paragraph. The determinant of a square matrix A is the sum of all of its signed elementary products. It is denoted DET of A, or simply put the A in absolute value bars. So in this context, this is what the DET is referring to. It means find the determinant, and it's going to be equal to the sum of these two signed elementary products. So the plus sign we don't need to bother writing, and we can just move this over and say A11 times A22 minus A12 times A21. And this is going to produce a scalar, which is called the determinant of this 2 by 2 matrix. Now there is sort of a visual way to look at this matrix and come up with this calculation, and that is to do the following. We multiply the entries on the main diagonal, and then we multiply the entries, the other two entries that are not on the main diagonal. We sort of do this crisscross product. And in the case of the main diagonal, we multiply by a +1. And in the case of the other two entries, we multiply by a -1. And notice that does give me the same formula that we have, A11 times A22, and keep that multiply by +1, keep the sign, and then subtract the product of A12, A21. So if I apply this crisscross method on this very specific example that we see here, I would multiply these two entries first. So the determinant of this matrix will be -6. And then I subtract, and then I multiply these two entries. And that's going to be a 20. So I'm going to basically subtract 20. And in the end, this gives me a determinant of -26. The determinant of a matrix will always be a scalar. All right, let's look at the 3 by 3 case. It gets a little bit more complicated here. It turns out there's going to be, if your matrix is 3 by 3, if it's n by n, there's going to be n factorial signed elementary products. So in this case, there should be a total of 6 elementary products. And let's go ahead and see if we can figure out what they are. Let's do the first one is going to involve the A11. Let's go to the second column, and I have to pick an entry that's not in the same row or column as the first one I've picked. So A22 is an option. And then the third entry that I must pick must not be in the same row or column that of any of the entries that I've already included. What this means is that this row and this column are no longer allowed to be used, and neither is this row or this column. So we're really forced now to just pick the A33 as my third entry involved in our elementary product. So one of our elementary products is going to be A11, A22, and I'm going to write them down so that the row indices are in increasing order, A33. And there's one of our elementary products. Now, if I insist on keeping A11 involved in my next elementary product, I did have some other options. I could have picked A32 as my next entry to include in my elementary product. And given the two I've already picked, notice what has been eliminated is options. So A23 is the only other option now. And here's 3 entries, none of which are in the same row or column as another. And so this is another elementary product. And again, I'll order it so that the row indices are in increasing order. So that means I would want to write A11, then A23, then A32. These are the only elementary products that involve A11. So now let's move to involving A21. One possible elementary product will involve A12 and A33 as well. None of these are in the same row or column as each other. But then write them down so that the row index is in increasing order. So I'm going to write A12, then A21, then A33. There was a second option that involves A21, and that would be to involve A32 and A13 instead. Writing these 3 entries down where the row indices are in increasing order would be A13, A21, and A32. And these are all of them that involve A21. And then finally, let's involve A31. One elementary product will be A22 and A13, so these 3 entries form an elementary product. But writing them in order so that the row index is in increasing order, I would write A13, A22, and A31. And then the final option in a 3 by 3 case, keeping A31 involved, would be to have A12 and A23 involved. And so we would have A12, A23, and then A31. Okay, so here's the 6 elementary products for this 3 by 3 matrix. Now we got to determine what signs they would be. And so let me give myself a little more space, and let's zoom into one of these at a time. Focus next on the column indices. So we have 1, 2, 3. This requires 0 interchanges of these numbers to order them. So that means that 0 is an even number, so this would be a positive signed elementary product. Let's look at the next one. Let's go down. So again, focus on the column indices. I'm going to go ahead and rewrite them because we do need to reorder. So we have a 2, 1, 3. In order to sort these, we need to do 1 interchange. This 2, 1 needs to be interchanged in order to sort the column indices. And so 1 interchange accomplished it, which means that, and 1 is an odd number, so this would be a negative signed elementary product. Okay, let's look at the second, or this third case here. We have these 3 numbers, 1, 3, 2, and I would just need to rotate interchange the 2 and the 3 to order them. So that's also only 1 interchange, so this would be a negative signed elementary product. And let's now go to this one down here. All right, let's see how many interchanges would be required to sort these. I'm going to go ahead and rewrite these indices, these column indices. To reorder these, I need to get the 1 in the first position, so I'm going to interchange the 1 and the 3. So 1 interchange gets me to this result, and then I need to do a second interchange to get the 3 and 2 sorted. So it took 2 column index interchanges to order these, and 2 is an even number, so this will be a positive signed elementary product. Okay, let's go to our fifth one. We have 3, 2, 1. All right, if I switch the 1 and 3, and only the 1 and 3, that would be an adequate interchange to sort these numbers. So that's only one interchange, and 1 is an odd number, so this would be a negative signed elementary product. And then finally, the last case, we have 2, 3, 1. To get this reordered, let me interchange the 1 and the 2. But it's not quite ordered yet, but now I got to interchange the 2 and the 3. So this took a total of 2, or an even number of interchanges, and therefore we have a positive signed elementary product. Okay, and then the end result, to find the determinant, we would simply add all of these signed elementary products together. Now it turns out that there is a visual way to get this answer, sort of a crisscross pattern like we did before. Looking at this 3 by 3 matrix, if I were to copy the first 2 columns of it and rewrite them, augment this with a rewriting of the first 2 columns. So we have A11, A21, A31. That's the first column repeated. And then repeat the second column, A12, A22, and A32. If you do this and then do the following crisscross pattern, so we'll do this main diagonal product, then we'll do this next diagonal product, and then this final diagonal product. And if I keep the signs of all of these 3 products, so plus, 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 this will account for the 3 positive sign products we had over here. Now, if we do these sort of reverse diagonal products, and we do a total of 3 of them, and you change the sign of each of these, or in other words, subtract these products, this will account for the 3 negative signed elementary products. Okay, let's apply that to finding the determinant of this 3 by 3 example here. I'm going to rewrite the first 2 columns and then multiply the entries on this diagonal, on this diagonal, and on this diagonal, and keep the sign of whatever I get. And then I will multiply the entries on these other diagonals, but change the sign of the product I get. And let's go ahead and see what this produces for us. Let's do the 3 greens first. We have 2 times 2 times 1. That's going to be 4, and keep the sign, so 4. We have 0 times 4 times 1. That's just going to be 0, so we get a 0 involved. We have 3 times negative 3 times negative 1. That's going to be positive 9, and keep the sign. And now let's do the 3 red products. We have 1 times 2 times 3. That's going to be 6, but change the sign, or in other words, subtract 6. So we say minus 6. And then we have negative 1 times 4 times 2. Well, that's going to be negative 8, but we're going to subtract negative 8. So that winds up being really plus 8. And then we have 1, negative 3, and 0. When you multiply those entries, you just get 0. So we'll just go ahead and write minus 0. And then you combine these numbers. We get 4 plus 9 is 13, plus 8 is 21, minus 6 is 15. And this would be the determinant of this 3 by 3 matrix. Moving forward in this class, you can just use these crisscross patterns to find your determinants. You don't necessarily have to think of this in terms of signed elementary products being added together. Also, as we get larger and larger matrices, it gets more and more complicated to calculate the determinant, because a 4 by 4 matrix will have 24, which is 4 factorial, signed elementary products. And they can be time-consuming to analyze all of them, whether they should be positive or negative. So we're going to introduce another technique that's used to find determinants of matrices that you can use for the 3 by 3 and larger, but we're going to demonstrate it for 4 by 4. Okay, so the next page. For larger matrices, it is convenient to calculate the determinant using a method called cofactor expansion, demonstrated below. Confirm your answer with technology. Okay, let's focus on this 4 by 4 matrix. I should have pointed this out earlier, but notice that the matrix, instead of being in square brackets, it appears to be in what are absolute value bars. Right? There's no little feet on these bars to suggest brackets. And when a matrix is in absolute value bars, you should be thinking, I need to calculate the determinant of this matrix, and this represents a scalar. Should have mentioned that up here when these 3 by 3s were in absolute value bars. But the 2 by 2s were in brackets, so I had to put the DET in front to suggest we were finding determinant. Okay, back to this 4 by 4 cofactor expansion. You begin by picking any row or column of this matrix. It's recommended that you pick a row or column that has the most zeros in it. So for us, that would either be the first row because it has a 0, or you can focus on the third column because it has a 0. And it doesn't matter which you pick. Let's go ahead and pick the third column. You begin by targeting the first entry in that column. So I'm going to put a box around what I'm targeting. And then, just like you're looking through the crosshairs of a gun, you'd cross out the row and column that 0 is in. Okay, so we put the number that we're targeting, which is 0, and we multiply it by the determinant of the 3 by 3 matrix that's not currently crossed out. So writing these entries down, it's -2, 1, 1, 4, 2, 3, and -5, 2, 5. And then we continue to target the entries of the matrix along the column or row I've chosen, in this case the third column. So I move down to that 2 position. I'm targeting a 2, so let's go ahead and write a 2 down. And then multiply this by a 3 by 3 determinant that's currently not crossed out. So that would be 3, 1, 3, 4, 2, 3, -5, 2, 5. And we continue to move down this column. So now target that 1. 1 times, and then the 3 by 3 matrix that's not currently crossed out is 3, 1, 3, -2, 1, 1, -5, 2, 5. And one more time, cross out that last one as well. 1 times a 3 by 3 matrix not currently crossed out, 3, 1, 3, -2, 1, 1, and 4, 2, 3. Now before we proceed, some of these coefficients we need to put a negative sign in front, and others we need to keep a positive. To know which should be a positive and which should have a negative in front, we create what's called a 4 by 4 matrix of signs. So make a matrix of signs by beginning with a positive sign in the upper left corner. And then you just do a checkerboard, basically. So the first row would be then minus, plus, minus. And then going down, we'll start with a negative, and then plus, minus, plus, and then positive, minus, and then negative, positive, negative, positive. This is called the 4 by 4 matrix of signs. It's a checkerboard of signs with a positive in the top left corner. And then basically we overlap that with this matrix here. Now, the only column or row that matter is the one that we've chosen for the cofactor expansion. So that would be the third column. So put these signs in front of these numbers in our work here on the right. So we have a positive in front of the 0, a negative in front of the 2, a positive in front of the 1, and a negative in front of that last one. This is the operation now that we will do to combine all of these determinants into one single number. Now the first one we don't need to bother with because multiplication by this 0 here in front is going to lead to a 0 result. So this is why you want to pick a row or column that has the most zeros. It reduces how much calculation you have to do. Now for the other ones, we have big 0 here, minus 2 times. For the other 3 by 3 determinants, you have to use the process that we illustrated up here to find each of these 3 by 3 determinants. So there's still more work to be done. But to speed things up, I went ahead and I calculated these determinants ahead of time. And so the determinant of this 3 by 3 matrix right here winds up being 31. And we write plus 1 times. The determinant of this 3 by 3 matrix here winds up becoming 17. And then minus 1 times, and then our final determinant winds up becoming -11. Now we just have to combine all these products. So we have -62 plus 17, and then plus 11. And that's going to give us -34. And this is the determinant of this 4 by 4 matrix. Now I could have picked any row or column to do this, and it will not change the answer. So for example, I could have chosen to do my cofactor expansion along the third row. I'm not sure why I would have picked that because there's no zeros there, but I could have. So we would target the 4 first. The 4 is in a positive position of the matrix of signs, so it would be positive 4 times the 3 by 3 determinant not crossed out. And then we would move over to the 2. This would be a negative position, so we do -2 times the 3 by 3 determinant that's not crossed out. And then we move here. This would be a positive 1 times the determinant of the 3 by 3 not crossed out. And then finally we would end on the 3, which is in a negative position, and it would be -3, therefore, times the 3 by 3 determinant not crossed out. And if you do it that way, in the end, you should still get -34. Now, let's confirm our answer with technology. So I'll go to the Desmos matrix calculator and enter in this matrix. I'll hit A, new matrix, add 2 rows, and add 2 columns, and then enter in these numbers. Then hit enter. Now hit DET button and enter the matrix A, and it confirms that the determinant of this matrix is in fact negative 34. Okay, let's go to the next slide. Calculate the determinant of A and of each elementary matrix E below. Then calculate the determinant of each product EA and generalize your findings. Okay, for this first case, we are going to multiply the 3 and the 4 and keep a positive sign, and then we will multiply the 2 and 5 and change the sign, and then combine those two products. And so we will say that the determinant of A, so put A in absolute value bars, is equal to 12 minus 10, and we get 2. Okay, let's do similar for each of these. So the determinant of E1, now all these E's are elementary matrices. They are the results of one row operation being performed on the identity matrix. We can probably identify what those row operations are. Let's go ahead and write them down real fast. This row operation is a doubling of the second row. So this would be 2 row 2 is how we went from I2 to E1. How we went from the second 2 by 2 identity to this matrix here. In this one here, we did a row 1, row 2 interchange. And in this case here, we did 3 row 1 plus row 2 to make a new row 2. So these are the 3 row operations associated with these 3 elementary matrices. Now let's find their determinants using the crisscross pattern. So in this case here, the determinant of E1 would be equal to 1 times 2, which is 2, and then minus 0 times 0. So we just get 2 minus 0, or just 2. The determinant of E2 will be 0 times 0 minus, and then 1 times 1. So we should get negative 1. And the determinant of E3 will do 1 times 1 minus, and then 3 times 0. So we should get 1 minus 0. We just get 1. We can generalize these statements. If the elementary matrix is produced by multiplying any row by k, then the determinant of that elementary matrix will wind up just being k. So if I had tripled row 2 to make E1, then the determinant would be 3. If you have an elementary matrix caused by doing a row interchange, it turns out that the determinant of such an elementary matrix will always be negative 1. And in the third case, if you use the third row operation, so that is replacing a row by adding a multiple of another row to it, then it will always turn out to be that the determinant of that elementary matrix is 1. Okay, now let's go ahead and calculate EA for each of these matrices, and then find the determinant of the result. And we're going to notice something. So let's calculate E1 times A. We created E1 by doubling row 2 of the identity matrix, so it's associated with that row operation. So E1 times A should just be the same effect as doing the same row operation, but on A instead. Or you can actually multiply these two matrices in this order and confirm this. But we should get 3, 5. First row doesn't change, but the second row gets doubled, and you should have 4, 8. Okay, let's go ahead and do all of the calculations of these matrices real fast. So E2 times A. This is effectively doing a row 1, row 2 interchange on the matrix A. So that's going to put 2, 4 up top and 3, 5 below. Okay, now let's do E3 times A. This will have the effect on A of basically doing the same row operation that was performed on I to produce E3. And so do that same row operation on A instead. And we do triple row 1, add row 2 to make a new row 2. So we're going to triple 3, which is 9. Add that to 2, makes 11. Triple 5 is 15. Add 4 is 19. And the first row stays the same. So that's just 3, 5. Okay, now we want to compute the determinants of each of these products. So the determinant of E1A, we'll do our crisscross pattern. So 3 times 8 is 24. And then minus 4 times 5, so minus 20. And we get a result of 4. The next case, the determinant of E2A, we do 2 times 5 is 10, and then minus 3 times 4, so minus 12, and that gives us the determinant of negative 2. And then finally, the determinant of the last product, E3A, 3 times 19 is 57, and then minus, and then 5 times 11 is 55, and 57 minus 55 is just 2. Okay, I want you to notice that when you do a row operation on a matrix A, and then calculate the determinant, that there are predictable results, predictable effects on the determinant. In the case of E1, E1 is associated with the row operation of doubling a row. If you do that row operation and then calculate the determinant, it'll have the effect of also doubling the determinant. In other words, the determinant of A was 2. And if I take that matrix A and double row 2, and then calculate the determinant, I should get a doubling of the original determinant. So I get a doubling of 2, and I get 4. Let's look at the case of E2. E2 is associated with a row interchange. So if you take a matrix A and do a row interchange and calculate its determinant, you should get -1 times the original determinant. So the determinant of A was 2. If you do a row interchange on A and then calculate determinant, you should get the opposite sign. So you should get -2. And then finally, the third row operation, this one's interesting. If you do the third row operation on a matrix and then calculate its determinant, it has no effect. The determinant was 2 in both cases. The determinant of A is 2, and then performing this row operation changed the matrix, but that it did not change the determinant. The determinant of the result is still 2. Furthermore, notice that in these cases that if I were to do the determinant of a product, I could really just break this down into doing the determinants of the two matrices separately and still get the same result. Right? The determinant of E1 is 2, and the determinant of A is 2, and then you just multiply those and you get 4. Here, the determinant of E2 multiplied by the determinant of A. The determinant of E2 is -1. Determinant of A is 2. Multiply those and we get the -2. And then finally, the determinant of E3 times the determinant of A. Well, if E3 is an elementary matrix by using the third row operation, its determinant will always be 1. So this is why we always just get the determinant of A again. In this case, we just get 2. Generalizing our findings. If you have a matrix A and you multiply a row by K, that will have the effect on the determinant of multiplying the determinant of A by K. If you have a matrix A and you do a row interchange and then calculate determinant, it'll change the sign of the determinant. And if you have a matrix A and you do the third row operation, it will have no effect on the determinant. Let's go to the next slide. Recalculate the determinant of the matrix below by first performing any number of row operations to get more zeros in the matrix before calculating the determinant. So we can do we can multiply rows by numbers, just keep track of how that'll affect the determinant. We can do row interchanges, just keep in mind how that's going to affect the determinant. Or we can do the third row operation as much as we want and have no effect on determinant. So that's what I'm going to focus on, doing the third row operation. And I want to try to get as many 1s and 0s in this matrix as possible before I calculate the determinant. So first thing I'm going to do is I'm going to do the third row operation of multiplying row 2 by 1 and then adding that to row 1 to change row 1. And that's going to put a 1 right here. So this will yield basically just adding row 2 to row 1. So we get 1, 2, 2, 4. And then the other rows do not change. Furthermore, I can actually put an equal sign because we're calculating determinants. And so I can say that the determinant of the matrix on the left is going to equal the determinant of the matrix on the right because I performed the third row operation, which has no effect on determinant. All right, we can keep this up. Now I'm going to focus on getting these 3 entries 0 by using the pivot 1 just above it. So we're going to do 2 times row 1 and add that to row 2, and then -4 times row 1 and add that to row 3, and then 5 times row 1 and add that to row 4. And this will result in a matrix that has the same determinant because we're only using the third row operation. So this time this is the top row that doesn't change, but the next 3 rows will. So 2 times row 1 add to row 2. That's going to give me 0, 5, 6, 9. The next row will be 0, -6, -7, -13. And then finally, we're going to get 0, 12, 11, and 25. Now, these numbers in this 3 by 3 submatrix that you're seeing right here are rather large, so we can continue doing the third row operation to sort of shrink them down. For example, we see a bunch of negatives in that third row. So if I were simply to do 1 copy of this third row and add it to the second row, that'll shrink the numbers down quite a bit. And then if I were to do 2 copies of that third row and add it to the fourth row, that would also shrink the other numbers down quite a bit. And this is still just me using the third row operation. So let's see what this gives me when all is said and done. This time it's the first row that does not change, nor does the third row. Adding row 3 to row 2 gives me 0, -1, -1, -4. And doing 2 times row 3 and add it to row 4 will give me 0, 0, -3, -1. Okay, I think I'm satisfied with the size of the numbers and the number of zeros. In particular, I was really focusing on getting this first column to have 1s and all zeros. And then I wanted to shrink the size of some of the other numbers. And I did all of this manipulation only using the third row operation. And now I'm in a position where I can calculate the determinant a little bit more easily using cofactor expansion. Now focusing on this 4x4 matrix, cofactor expansion, we're going to target the first column because it has a 1 and a bunch of zeros. So we have the 1 in the top left position. That's a positive position as far as the matrix of signs is concerned, so just a positive 1. And multiply this by the 3x3 determinant of the matrix that's not currently crossed out. Okay, because of all the extra zeros I put in here, when I move my target down the first column, we're just going to have 0 times a 3x3 matrix, determinant of a 3x3 matrix. Again, 0 times another determinant, and then again 0 times another determinant. So I don't even need to bother with the remaining calculations. It boils down to this calculation, which is positive 1 times a 3x3 determinant. And I'm going to use now our crisscross pattern to find this determinant. So I'm going to copy the first 2 columns. Then I will multiply this diagonal, and then this diagonal, and then finally this diagonal, and keep the sign. So I'll put plus, plus, plus. And then I will multiply the other diagonals, but change those signs. And all of this will be times a positive 1, which I don't really need to write, but I'll go ahead and put it there. We have negative 1 times negative 7 times negative 1. That's going to be negative 7, and keep the sign, so negative 7. We have negative 1 times negative 13 times 0. That 0 simplifies things. Don't need that. We have negative 4 times negative 6 times negative 3. This is going to be a negative 72. And those are the 3 green products, keeping their signs. And now let's do the red products. The first one involves a 0, so we don't need to write that one. The next one is going to be negative 3 times negative 13 times negative 1. That's going to be negative 39, but then change the sign to positive 39. And then finally we have negative 1 times negative 6 times negative 1 is going to be negative 6, but then change the sign to positive 6. All right, then we can go ahead and continue to simplify with the 2 negative numbers combined to be negative 79 and the 2 positive numbers combined to be positive 45. And when I add these, I do get negative 34. Notice that was the determinant that we got up above. All right, so this strategy of getting more 1s and 0s and shrinking the numbers if necessary by using only the third row operation is a great strategy because it can simplify your calculations by hand, and it has no effect on the determinant of the matrix. Let's go to the next slide. Complete each statement below. Note that D is a diagonal matrix. Okay, now I'm not going to necessarily prove all that we're about to say. We might make a few arguments for some of them or a few justifications. But here we go. If you have the determinant of a square matrix and it's not 0, it means that that matrix is invertible. And notice this is a double implication arrow. So these 2 statements are equivalent, meaning that if the matrix is invertible, its determinant will be non-zero, and vice versa. If the determinant is non-zero, it means the matrix will be invertible. So if either one of these is false, then so is the other. So if you have a matrix A that's singular, not invertible, then its determinant will be 0. All right, the next case, if you have the determinant of a product of 2 matrices, it turns out that you can find their determinants separately and then multiply the results. We actually sort of saw that happening up above in the case where one of the matrices was an elementary matrix. Turns out it's always true. Let's keep in mind that A is n by n, so maybe we should specify that for this next one. Let's say that A is n by n. Now when you multiply a matrix by a scalar, you multiply all the rows by that scalar. You multiply every entry by that scalar. So that's kind of like doing n row operations of multiplying by k. And every time you do a row operation of multiplying a row by k, then you multiply the determinant by k. And since this has n rows and each row got multiplied by k, you're going to be multiplying by k n times. So basically, this winds up being k raised to the n times the determinant of a. Now the determinant of a sum. It's tempting to guess that that determinant will be the sum of the determinants, but it turns out that's not the case. So let's go ahead and put a slash through this one. The determinant of a sum cannot be broken down into the sum of the determinants. So be careful about that. There are cases where this is true, but in general it's not true. Now when you do the transpose of a matrix and then calculate its determinant, it turns out that that has no effect. So that's the same thing as the determinant of A. This next one, let's justify that after we justify the determinant of an identity matrix. The determinant of an identity matrix, so let's just look at a 3x3 identity matrix real fast. The only elementary product here that doesn't involve a 0 will be the product of the main diagonal, the 1, 1, 1. And that's going to be a positive signed elementary product. So it's just positive 1 is the determinant of an identity matrix. That's always the case. So the determinant of an identity matrix is 1. For that matter, the determinant of any diagonal matrix. So if you have like D11, then D12, then D13, and these are the only non-zero entries, and maybe they're zero themselves, but the only elementary product here that doesn't involve a zero will be the product of the main diagonal, and it's a positive signed elementary product. So you just multiply the main diagonal. So we'll say the product of the main diagonal entries, the product of the di sub i's. Okay, let's go back up to the determinant of an inverse matrix, and I want to justify this one here. This one's pretty easy to justify. If you have a matrix times its inverse, we know that that will produce the identity matrix. So if you want to find the determinant of this, you just determinant both sides because they're the same matrix. And on the left, we can break down the determinant of each matrix separately, and the determinant of the identity matrix is 1. So solve this for the determinant of A inverse, and we get that it has to be the reciprocal of the determinant of A. So that's what we want to write here, 1 divided by the determinant of A. And finally, if you have A to the n and you want to find its determinant, well, let's think about A cubed real fast. A cubed just means do A times A times A. And so if you find the determinant of A cubed, you can do the determinant of each of these separately, which is just a generalization of the second statement right here, that the determinant of a product, you can do the determinant of the factors separately, which really just means that we're going to do the determinant of A, but then cube that result. So we just, in other words, the power can just be put after the fact of doing the determinant. Okay, now I want to revisit the equivalence statements by looking at this statement right here, that if the determinant of A is non-zero, that means that the matrix A is invertible. This allows me to add a 7th statement to our list of 6 equivalent statements. So now we have 7 statements that are all equivalent, meaning if one of them is true, all of them are true, and if one of them is false, all of them are false. And the determinant gives us a powerful tool to determining whether a matrix is invertible. Okay, let's go to the next slide. Consider the formula below for finding the inverse of an invertible 2x2 matrix. I'm not going to prove why this is true, but it does give you a little shortcut for finding inverses of 2x2s. So we have a 2x2 matrix, and if you want to find its inverse, you do the following formula. You do 1 divided by the determinant of the matrix. So this will be a scalar right here, multiplied by this rearranged matrix, and this will give you the inverse. Now notice what's been different. Let's do some highlighting. A22 is now in this position, and A11 is now in this position. So the main diagonal flip-flopped. And then the other thing to notice is that A12 and A21 are in the same positions, but you change their signs. Okay, let's apply this to finding the inverse of these 3 2x2s. First case, you want to find the determinant. The determinant of this matrix A. We'll do the crisscross pattern, so we do 3 times 2 is 6, and then minus 5 times 1, which is 5. So we get a determinant of 1. Now this is non-zero, which means that the inverse exists. So we can go ahead and calculate the inverse. The inverse matrix will be 1 divided by the determinant of the matrix we just found. So I'll change that to a 1 here in a second. Multiplied by a 2x2 matrix where the main diagonal flip-flops. So they get interchanged. So we put a 2 here and then a 3 there. And the other entries change sign. So a -1 there and a -5 here. And then we continue. The determinant of the matrix A is 1, so we really just get a 1 here in front of this matrix, and we multiply the matrix by 1, which means you multiply every entry by 1, which isn't going to change anything. So just like that, we can also calculate the inverse of a 2x2 matrix that's invertible. I will leave it to you now to verify that if you multiply these two matrices, you get the identity. Let's look at the matrix B. Calculate its determinant first. So 2 times -3 is -6. And then minus, and then 6 times -1 is also -6. So we do minus -6. That's going to wind up being plus 6. And we get 0. If we get 0 for the determinant, then there is no inverse. So we say B is singular, and there is no inverse. So B inverse DNE. It's not invertible. You'll notice that the formula would also fall apart here because you can't divide by 0. And now let's look at matrix C. The determinant of matrix C is equal to 6 times 4 is 24, and then minus 4 times 5 is 20, so 24 minus 20, and we get 4. This is a non-zero number, so that means the inverse does exist. And C inverse will be found by doing 1 over this determinant we just calculated, so 1 over 4 times, and then we'll rewrite our matrix here. The 6 and the 4 on the main diagonal will switch places, so 4 then 6, and the other two entries will change sign, so -5 and -4. And then to finish this out, we could stop here technically, but let's go ahead and distribute the 1/4 across the matrix. we're going to get 1/4 times 4 is 1, 1/4 times -5 is -5/4, 1/4 times -4 is -1, and then 1/4 times 6 is going to be 3/2. And this is our inverse matrix, and I will leave it to you to verify that when you multiply these two matrices, C and C inverse, that you do get the identity. And then our final slide. To solve a system AX equals B, where the coefficient matrix A is invertible, we can use a method called Cramer's rule, as shown below. Okay, let's convert this system to matrix form. The coefficients of U and V in the first equation are 6 and 5, and the second equation are 4 and 4. This would be multiplied by the variable vector of UV and set equal to the constant vector of 2, -1. Now we have many ways we can solve this. Turns out the coefficient matrix is invertible. Its determinant is non-zero. We just showed that in the last slide. So we could use an inverse matrix to solve this, or we could use substitution elimination methods, or I could use an augmented matrix, put it in reduced row echelon form. So there's already several ways we have to solve the system, but here's yet another way called Cramer's rule. Also notice that because the coefficient matrix is invertible, our equivalency statements suggest that this system is not only consistent, but that's going to have a unique solution. And Cramer's rule will help us find that unique solution as follows. The first variable u can be found by calculating a quotient of determinants. And that quotient of determinants is as follows. The denominator determinant will be the determinant of the coefficient matrix itself. So 6, 5, and 4, 4, find its determinant. And the numerator will be a 2 by 2 determinant calculated as follows. So you take this 2, -1, the constants, and you replace the coefficient matrix U column with those numbers instead. So we're going to put a 2, -1 in the U column, and the V column leave alone. So 5, 4. To find the variable V, we'll do something very similar. We're going to do a fraction of determinants. The denominator determinant will still be the same, which is just the determinant of the coefficient matrix. And for the numerator determinant, we're going to take this 2, -1 and replace the V column of the coefficient matrix with them. So the U column will stay the same, it'll be 6, 4, but the V column will become 2, -1. And this is one way that we can get the solution to the system. Let's go ahead and actually calculate these determinants. We have 2 times 4 is 8, and 8 minus -5 is 8 plus 5, so we get 13. And then we have 24 minus 20, or 4. So 13/4 is the U value. And the V value will be, we do 6 times -1 is -6. -6 minus 8 is going to be -14 over this 4. So you could simplify this one to -7/2. And this is our solution to the system. U has to be 13/4 and V has to be -7/2. I'll leave it to you to verify that. And this process generalizes to larger systems as long as the coefficient matrix is square and invertible. So here we have 3 equations, 3 unknowns. Let's go ahead and write this in matrix form. And the coefficient matrix will go x, y, z in that order. So it's going to be 2 and -2, and z is 0. X, y, z of the second equation will be 1, 0, 1. And x, y, z of the last equation will be 0, 1, 2. And then we multiply this by the variable vector of x, y, z, and set this equal to the vector of constants. Now that 3 does have to be added over, so we do have 1, 4, 3. Okay, let's go ahead and just call this coefficient matrix A, moving forward. And so the x variable will be found by dividing 2 determinants, 3 by 3 determinants. The denominator will be the determinant of whatever the coefficient matrix is, but then the numerator determinant will be calculated, or the matrix will be formed as follows. Take the 1, 4, 3, and replace the x column with those numbers, and then rewrite that 3 by 3 matrix otherwise. So we would have a 1, 4, 3, and then the other 2 columns, the y and z columns, are unchanged. Y will be similar. I'm going to copy paste. The denominator determinant will still be the determinant of A. The 1, 4, 3, though, will now be thrown into the y column, and the x column will be the original x column. So looking back at the original x column was 2, 1, 0. So it's just the y column that gets replaced by the constant vector, the 1, 4, 3. X and z columns stay the same. And then finally, we can find z doing something similar. The denominator will still be the determinant of A, but now this 1, 4, 3 will be moved over to the z column, and the x and y columns of the original coefficient matrix will be unchanged. Okay, then I went ahead and did all of these calculations, all of these determinants ahead of time, but you can do them by hand. It would be a little bit more calculation you have to do, or you can use technology to speed this up. But when you do this correctly, you should get the following results. The determinant of A was 2, and the determinant of my first numerator is 9, determinant of my second numerator is 8, and the determinant of my final numerator is -1. And so we have answers of 9/2, 4, and -1/2. I leave it to you to verify that these are in fact solutions to this system. And this wraps up our lesson on the determinant of a matrix.